As we've seen since the beginning of this series, logic is a tool for verifying arguments, which has been honed even since before it was properly established as a philosophical school with Aristotle. Though Aristotle settled the main version of logic that was to be used for more than 2 millennia, the many developments and iterations of his interpretations conjoined later alongside those of mathematics itself, leading to Frege's revolution in how we study and apply logic. Even so, nowadays we have already adapted Frege's theory further, which is why we've avoided utilizing his original symbols, so as to not get confused with the ones currently used. Now then, let's go further into the current state of logic with an overview of most of its main areas and concepts. First, let's reiterate some areas and concepts in logic which are still currently used. Logic can be divided into formal and informal logic. Formal logic refers to the symbolic logic we've seen so far, focusing on given formats and structural analysis, while informal logic refers to the verbal arguments used in everyday life. While for all x, yx, then mx is a proposition written in formal language and thus refers to formal logic, all YouTubers are mortal, or any other formulation within these variables, such as every chair is red and the entire vehicle is material, is a proposition of informal logic, being a part of what is called natural language, referring to our common spoken language. Within formal logic, there's the proper philosophical logic, the original one, as well as mathematical logic and computational logic. Though the latter two both dialogue frequently between themselves and the former, we will not deal with them right now, as our focus is philosophical. The different kinds of logical analysis within philosophical formal logic are term logic, established by Aristotle and focusing on individual terms; propositional logic, established later in antiquity with the dialecticians and Chrysippus, which deals with the relations between whole propositions instead of single terms; and predicate logic, or first-order logic, which was invented by Frege and mixes the previous two, and is also widely used within mathematics and computation. There are many other kinds, such as fuzzy, hybrid, relevance, and provability logic, developed in the latter half of the 20th century and not strictly related to philosophical logic. Others can be understood within the framework of the ones we'll cover, such as modal logic, which deals in non-absolute quantifiers such as many, few, and rarely, as we've previously seen. Regardless of which kind of formal logic we're looking at, they all deal with arguments, or inferences, which usually contain at least two premises and a conclusion. Every A is B, all P is Q, and for all x, yx, then mx are but sentences within these different perspectives and can be used as a premise or a conclusion, depending on their context. Arguments can be true or false, and independently they can also be valid or invalid. Logic focuses on the formality of arguments, and thus a logically true argument has no bearing on the ontological or epistemological status of an inference. All dogs are cats, all cats are hippos, thus all dogs are hippos, is a valid argument regardless of the language we use to represent it, even though we know that none of these premises nor the conclusion are truthful. With this in mind, we are able to abstract a logical calculus toward a more mathematically driven perspective. To this end, an important background theory of logic is set theory, a branch of mathematical logic introduced by Georg Cantor in the 1870s, widely used to represent logical meaning. As we've seen before, when utilizing the universal positive mode in an Aristotelian proposition, all A is B, it is analogous with representing a group A completely within a larger group B, and the same happens with the contemporary predicate logic example. Thus, terms or propositions would be members of sets, or as Russell and others refer to them, classes, and some of these would either be inserted in others or contain the entirety of others, or even overlap with others, besides not touching others at all. This would be the foundation upon which Leibniz first developed the idea that logical truth and arithmetic truth could be related, since it is usable in both fields almost interchangeably, and thus became the background onto which most current-day logic is developed. Though Aristotelian logic is still relevant and used in some situations, whether in its term or propositional manners, it has predominantly given way to the more sophisticated and comprehensive post-Fregean predicate logic. And since we've already spent several tutorials analyzing the foundations and developments of the former, we can focus on the latter in this tutorial. An important note, however, is that Aristotelian logic, or classical logic as it became known, still had many developments within the last century and became much more sophisticated, remaining to this day a strong alternative for the analysis of reasoning with a much more intuitive and still effective method, though invariably limited when compared with predicate logic. Predicate logic is referred to as first-order logic as it represents the original logicist intent of providing the most elemental structure for propositional analysis in formal logic, and so it is at its core a symbolic system. Though many already existed before modern logic in mathematics or elsewhere, most of these symbols were created by the mathematician Giuseppe Peano, and their application in logic was introduced by Frege, Russell, and others. We've already seen what some of those symbols are. The turned A, the universal quantifier operator, the right arrow, which signifies an implication or material implication, Y, M, and other capital letters, which represent universal predicates, the lowercase x, which is a variable representing an indeterminate member of such predicates, and the lowercase d, referring to me, or a determinate member of such predicates. Now, these last two are not static. As we previously stated, we used the lowercase d to represent my name. To avoid confusion with variables, usually the indeterminate ones are later letters of the alphabet, like X, Y, and Z, and determinate ones are the first ones, like A, B, C, and D. These, of course, refer to the universal positive mode we were using before. If we were to say that I am not a YouTuber, we can use tilde or this symbol, which refers to a negation, not YD. And when we refer to particulars, or only to some members of a group, we use sideways E, or sideways E with an exclamation, to signify a single exclusive member. Other important symbols are the upwards wedge, or ampersand, called conjunction, representing and in a sentence. Its opposite, downwards wedge, called disjunction, which represents or. The two-way arrow, called the equivalence, sometimes shortened to if, where the inference is true if and only if both predicates are either true or false, and its opposite, the two-way arrow with a slash, or V-bar, called the exclusive disjunction, shortened to XOR, where the inference is true if and only if either one of the sentences is true and the other is false. There's also parentheses, which aggregate sentences and indicate that whatever is inside them must be solved before progressing to the rest of the inference, besides a few things we'll see in the next tutorial. And this symbol, which merely represents the line between the premises and conclusion of a vertical calculus in a horizontal manner. Let's see a few examples using these symbols. Some students are hardworking while others are lazy, represented this way, which can be read as there is something X that is a student that is either hardworking or lazy. Since we are referring to a part and not all of students, as there might be some in between hardworking and lazy, we use the particular, and the exclusive disjunction is used, since they can't be both at the same time. Another example would be, if it's raining, I never wear flip-flops, represented this way, which can be read as there is one specific X that is Dave, that if it is the case that it is raining, X does not wear flip-flops. Since we're talking about a specific individual, me, and not all or some Daves, we use the exclusive particular with the determinate member D and a negation to Dave uses flip-flops, FD, when it is raining around me, RD. More and more, the image of a purely symbolic logic, almost indistinguishable from mathematics, becomes clearer. In the next tutorial, we'll see some other concepts and advanced calculus that is possible with these basic ideas and symbols, and then proceed to identify some argumentative fallacies they help solve.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.